everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. Curves are really central to calculus because they represent motion and they represent all kinds of interesting geometrical constructions. And it's very natural to ask certain questions about them, questions having to do with areas formed by curves and also tangency kinds of questions. And these really have motivated people's study for thousands of years. And today we want to go back to antiquity and introduce some of the fundamental curves that were studied by the ancient Greeks and that still are motivating and very important for understanding modern calculus. So calculus is, in some sense, the study of curves. And so we want to get familiar with some curves because they are going to be the objects that we're ultimately interested in finding out about. Okay, so the curves in calculus have a kind of a geometrical or a physical or mechanical aspect. There's sort of these two sides of thinking about curves, just as there are these two sides of calculus that I've talked about, the geometrical and the physical side. Now, when we go back to antiquity, the real subject starts with two fundamental curves. One is so fundamental it's often not considered a curve, but it really qualifies, which is the straight line. Absolutely, key ingredient in geometrical constructions. And the other one, of course, is the circle, regarded by the ancient Greeks as a kind of perfect mathematical object. Unfortunately, there's already a lot of complication going from the line, which is reasonably understandable, but still has a lot of subtlety, to the circle. And so there's this sort of tension in calculus also between the linear and the curved as represented by the circle. So it's really fascinating, these two fundamental curves that both figure at the heart of the subject and that also lead to some fascinating tension that sort of pervades the subject. So if we believe in the beauty of the circle and the line, then what more natural thing to do than to try to put them together? And that's what the Greeks did to get the sort of next most important family of curves, which are the conic sections. So they thought in terms of three dimensions, and they said, well, here's a circle, and here's a line. So suppose we have a fixed point, and we join the fixed point with the circle. Then this line will trace out a surface, and that surface is a cone. And strictly speaking, because the line actually extends beyond the point where I'm holding it, this cone also has a portion of it that's below the hand. So that's an important aspect of this as we study these conic sections. So here is our cone, which is like an ice cream cone, but it has a top and a corresponding bottom as well. And so this is a very natural three-dimensional object. And the Greeks said, okay, let's slice this thing with a plane to get a planar curve. And if we slice it like this, then we get an elliptical cross-section, so an ellipse. If we slice it with a plane sort of like this, the blue plane, then it will meet both the top and the bottom portions of the cone, and that will give us a hyperbola with two sort of separate branches. So we'll cut out a piece of the cone there and also cut out a piece of the cone there. And then kind of halfway, or just between these two cases of the ellipse and the hyperbola, if we take this plane here and kind of rotate it until we get to the blue one. At some intermediate point, like right here, it's going to be parallel to one of the generators of the lines of the cone. And what happens then is that it intersects only half of the cone, but it does so not in a finite curve like this, but in a curve that is unbounded, and that is the parabola. So that happens only really in a very special kind of situation. You have to get it exactly right for that to happen. You move it a little bit more and it intersects the top part and you get a hyperbola. You move it a little bit less and it intersects not sort of infinitely, but in a finite cross-sectional ellipse. So the parabola is kind of poised very delicately between the families of ellipses and the families of hyperbolas. Now, These conic sections are incredibly beautiful, and this was recognized by Apollonius, who was the great geometer of the ancient world, and he studied the conics in great detail and discovered all kinds of fabulous things about them. So they're beautiful geometrical objects, but they also turn out to be really important for practical applications. And it turns out that they are actually very, very important for calculus. So we are going to have to become a little bit familiar with these remarkable curves and some of their properties. Now, Apollonius realized that these conic sections also had a completely different kind of manifestation in terms of what are called loci. Or another way of putting it is that they can be described metrically, that is, by using notions of perpendicularity as well as distance or square distance. So to see how that goes, what we do is we introduce a fixed line, say L, which is called the directrix, and a fixed point F, which is called the focus. And in terms of these two initial quantities, we then consider the locus of a point X, which satisfies a certain metrical relation with regard to F and the line. So if we look at this X here first, so this point X here, which is on this red ellipse, has the property that its distance to the focus and its distance to the line, when I say distance to the line, I mean the perpendicular distance, okay? These two are in a certain ratio. So this distance over this distance is in the ratio of 1 to 2. And this property, this kind of a locus property, characterizes the ellipse. So the ellipse is then the path of all the points X which satisfy this property. So if X is over here, for example, then this distance is also still twice the perpendicular distance. Up to X being out here, then this distance should be twice this distance. So this property, which is a metrical property because it involves distance, if we wanted one involving rational trigonometry, which I'll tell you about at some point, then you would square this, and that would actually be algebraically a little bit nicer. But this is the classical way that Apollonius thought about it. So the ellipse is characterized by this ratio being actually a number less than 1. If we look at the case of a parabola, that turns out to be the case when this ratio is exactly equal to 1. In other words, when the distance from the point X to the focus exactly equals the distance from X to this line. So this is the green locus, that's the parabola. So all of these points have the property that their distance to the focus and their perpendicular distance to the line are all equal. Roughly, this is just a hand-drawn diagram. And then on the other side, we have the hyperbola, which is characterized by this ratio being a number bigger than 1. For example, 2. So here's the hyperbola, and here's a point X, and the distance from X to the focus compared to the distance from X to the line. So the ratio of 2 to 1. Now, if you think about this, so there's kind of you can see the way that the parabola is exactly between the cases of the ellipses. So if we change this number here to some other number between 0 and 1, then we get a whole family of ellipses. And if we change this number here to another number bigger than 2, we get a whole family of hyperbola. And so the parabola is exactly balanced between those two families. But the hyperbola we need to say a little bit more about, because actually what we have here is not the entire story. Because it's also possible for there to be other points that satisfy this same property, that xf over xl is equal to 2. For example, suppose that we went over here an equal amount, so over here somewhere there, then this point is also going to have the property that the distance from x to f is twice the distance from x to the line. And that means there will be another sort of branch of the hyperbola over here, which is what we expect from the description as a slice of a cone. There's these two branches. So this metric condition actually does capture both branches of the hyperbola. So that's the full story in this case here. So this is a very lovely story that again goes back to Apollonius. And I mean, these curves are just so full of interesting things. Apollonius discovered dozens, if not hundreds, of interesting facts about them. And unfortunately, a lot of these are not really that well known. But in this course, we'll have a chance to meet quite a few interesting properties of these fabulous curves. And we'll see that they are, in fact, very, very important for calculus. So these curves are intimately connected with calculus. The importance of the conic sections and their sort of central role in not only geometry but also mechanics and many other branches of mathematics, including calculus, really becomes, I guess, more understandable when we move to the 17th century and the remarkable insights or developments contained in analytic geometry due to these brilliant French mathematicians, René Descartes and Pierre Fermat. So Descartes wrote a very influential book called La Géométrie in 1637. And in fact, in that same year, Fermat wrote an essay called Introduction to Plane and Solid Loci. But it was only actually published officially later on. But basically, these two gentlemen both understood, sort of at the same time, the power of using Cartesian coordinates to understand and revitalize the Greek study of curves. And they both understood that a linear equation, like ax plus by equals c, that we've already talked about, represents geometrically a line somewhere in the plane, once we've set up x and y coordinates. But much more interestingly, perhaps, is that a quadratic equation in x and y, in other words, an equation of the form ax squared plus bxy plus cy squared plus dx plus fy equals g, these are all constants, x and y are the variables. This is of degree 2, so there's quadratic terms and linear terms and constant terms, but altogether that's of degree 2. That such an equation determines a curve in the plane, which is exactly one of the conic sections of Apollonius. In other words, an ellipse, or a parabola, or a hyperbola, or perhaps some kind of degenerate case. For example, it might be a product of lines. Okay. So from the algebraic point of view, so this really clarifies that the conic sections are necessarily going to be important because they correspond to quadratic equations. In our algebraic setup of the Cartesian plane, lines are linear equations and conic sections are quadratic equations. So of course they are going to be important. It's the next natural step up from the lines. But it's a big step up, both geometrically, arithmetically, and when it comes to calculus. A natural question, which is a very interesting one, is, so given one of these quadratic equations, someone writes down some polynomial of degree 2 in x and y, how can you tell whether it's an ellipse that you're looking at, a parabola, or a hyperbola, or perhaps some degenerate one? And how can you tell the special case of the circle, which is a special kind of ellipse? That's a very interesting kind of question, which is very natural in the direction of calculus. So we'll have a little bit of thinking about that as well. So we see that the ancient Greek study of curves was in some sense revitalized by the introduction of analytic geometry and being able to interpret these curves as algebraic objects, not just geometrical ones. All right, so we have this meeting, this convergence between the geometry and the algebra. And that's really, that's really empowering the calculus and really motivating it. By and large, the ancient Greeks had a rather static view of curves. So they thought of them as loci, but they didn't necessarily think of them as something moving physically. That was, generally speaking, more of a 17th century point of view where the Newtonian fascination with dynamics and physics and laws of motion became much more important. However, in the ancient Greek times, there were some exceptions and some very notable ones. And Archimedes was very physically oriented, sort of a genius whose accomplishments extend in lots of different directions. So he was very interested in physics and motion as well. And one of the curves that he studied in a book called On Spirals is now called the Archimedean Spiral. And what it is a combination of the motion along a line and motion around a circle. In fact, uniform motion around a circle is sort of combined with uniform motion along a line to give this spiral. So how does that work? Well, it's very simple, really. He thinks of a line, or perhaps a ray, emanating from some fixed point. And he imagines this ray rotating uniformly around the point O. Okay, so it just goes around uniformly. And it keeps on going. And simultaneous to that motion, there is a point on the line which is moving uniformly away from the fixed point O along the line. So here it's at that point there, and when the line has got up to here, the point has moved up to there, let's say. And then after an equal amount of time, it's gone twice as far, it's there, and then 3 times as far, and then 4 times as far, and then it's over here, and then it's over here, and it's over here, and it's over here. And you can just keep on imagining extending this. It will just keep moving out there, and it would trace out this ever-increasing spiral, which is getting bigger, but it's not getting bigger that much. It's basically a linear motion in terms of distance from this fixed point O. So this is a very nice curve that Archimedes studied, and he, in fact, asked some very natural questions about it, which are very motivating problems for the calculus. He asked questions like, how do you tell what the area of a portion of this thing is? Like, suppose that we just chop it off there and ask, what's the area of that piece there? Can we calculate that? Another kind of question he asked is, like, suppose you take a point on the curve, how do you actually calculate a tangent or find a tangent to the curve at that point? Now, these are the motivating physical problems for the calculus. So you can see that Archimedes was already thinking very much in a kind of a modern point of view. Archimedes was so far ahead of his time. And a lot of the calculus really sort of is intertwined with his thinking. And probably if we knew all of his works, because we don't have all of his recorded works, probably his pivotal role in understanding aspects of the calculus would become clearer. Anyway, so it's interesting that he's studying curves, he's studying areas, he's studying tangents, and this is a beautiful example of a somewhat non-trivial but still sort of fundamental and interesting and basic kind of curves, because it's combining these relatively simple motions. So another kind of notable curve from antiquity is called the Conchoid of Nicomedes, which is also around 200 BC. And the situation there is that we have a fixed point, call it F, and we have a fixed line, call it L. And we're considering secondary lines that are passing through F and meeting this fixed line L at various points. So at any one of these given points, let's say there, one there, what we're going to do is we're going to mark off from this point along this line a certain segment of a certain fixed distance. And to be fair, we're going to mark it off on both sides. So R in that direction and R in that direction down there, let's say. Okay, so we mark off an R there and an R there. And we do this for as many of these lines as we have patience with. So there's another line. So we mark off the same R from the point of intersection up and another down. And there's another one. So we mark off an R and an R. And so then as this line is moving, this top intersection is going to trace out some curve. We're going to go like that. It's going to be sort of asymptotic to the line as you go in that direction. And then the bottom one is also going to do something which is a little bit different. It kind of has a little curl there. You can kind of check that. Of course, it depends on the value of R with respect to how far the focus is from the line. But in this case, it will do something like this. We get this curve that has a portion of it like this and also a portion like that. It's kind of a pleasant thing. And it's an example of a geometrical locus. So something is moving and something else is moving, and then some intersection is tracing out something else. And there's all manner of rich kind of curves that you can generate this way. In particular, you can play this conchoid game with actually any curve that you have. So you don't have to start with a line. You can imagine having something else instead of that line, still having a fixed point, and then playing the same game of drawing lines through the fixed point, seeing where you meet the curve, and going a certain distance on either side of the given curve. You would get another family of curves, which you could call a conchoid of the given curve that you started with. So it's actually a rather general kind of construction, and it actually has some theoretical uses in terms of some classical problems that the ancient Greeks wrestled with. It's a nice example of a curve. So another exception to the general idea that the Greeks were mostly interested in static curves and loci is the work of Ptolemy in the direction of astronomy. Because of course the motion of the planets in the night sky was a fundamental concern to a lot of ancient peoples, and in particular to the ancient Greeks. And when you're studying the night sky and the motion of the planets in particular against the background stars, that what you observe is that the motion of, say, something like Mars, it's not entirely straightforward. It's sort of moving along the ecliptic, there's sort of this plane which the sun moves also. But it doesn't necessarily move at a uniform rate. It kind of slows and then it goes backwards a little bit and then it carries on again. So it kind of does this motion, and it's moving generally in this kind of direction, let's say, but it often sort of stops and goes back and then carries on again. So Ptolemy had a theory about this, and he said, okay, that what's involved here are some curves called epicycles. And again, interestingly, these were also based on circles, because the ancient Greeks thought the circle was perfect, and the world was perfect, so it makes sense that the world is explained by circles. You know, there's a mathematical unity of theory and practice. So here is the Earth. So in Ptolemy's theory, the Earth is the center of things. And so here is the planet Mars, and Mars is going around the Earth, or it may appear to be so. Okay, so how do we explain its motion? Well, Ptolemy said, okay, let's look at a circle, a big circle around the Earth, which is more or less the trajectory of the planet Mars. But along this circle, we're going to imagine a smaller circle, which is itself kind of moving. So this blue circle is moving, okay? Moving. But Mars is on this blue circle. So the blue circle is moving, but Mars is actually going around on this blue circle. So it's going around uniformly on this smaller circle, while the blue circle is going uniformly around the bigger circle. So we have this combination of two different circular motions. So the effect of that is that, you know, Mars will kind of have this motion, some kind of looping motion like this. It'll kind of loop around the big circle due to the interaction with the smaller circle. And Ptolemy was able to adjust the parameters, and he adjusted things and adjusted the centers a little bit so that this actually matched up reasonably well with what was actually observed, not just for Mars, but for the other visible planets too. So it was actually quite a tour de force in terms of a geometrical explanation for a very important direct observational aspect. So, you know, introducing the idea that the laws of nature are somehow captured by some mathematics. That's already happening in the ancient Greek times. And of course, in the 17th century, that really blossomed to much greater extent. But already Ptolemy, and that was the major theory of astronomy really for about 13 or 1500 years, until the Copernican revolution came along in the 1500s and 1600s. So that's another example of an important kind of curve, an epicycle, which is really built up from circles. So these are just some of the curves found in Antiquity. There are others too, and in the course we'll have a chance to meet some more. And we also really want to spend a little bit more time on the conic sections. So the conic sections are particularly important, and their properties are particularly crucial for some aspects of calculus. So there's a lot to learn. I'm Norman Wahlberger. Thanks for listening.